b equals c to satisfy each of these four conditions. Number one, we're being told that c will equal a negative number. So what we need to do is we need to choose a value for a and b where the c value will be negative. So an example would be log of 1 over 10 equals negative 1. Now in this case, you see I don't have a base of this log, so we have to assume that this is going to be base 10. Now in general, c will equal a negative number whenever your b value is between 0 and 1. So the b value that you choose, it has to be between 0 and 1 in order for c to be a negative number. Now taking a look at number 2, c will equal 0. So again, we're thinking choose a value for b here, choose a value for b where c is going to be 0. Well here this is going to be log of 1 equals 0. And again, I don't have a base here, so we're going to assume that this is log base 10. Now, c will equal 0 whenever your b value will equal 1. Next is number 3. Number 3, c will equal 1. Here, my example will be log of 10 equals 1. And again, our base is 10, so we're thinking log base 10 of 10 is equal to 1. Another example we could have would be log base 2 of 2 equals 1. So c will equal 1 whenever your a value, in this case a is your base, will equal b. And then finally, number 4, c will not exist. My example is log of negative 10. So this is one example where c will not exist, but in general, c will not exist whenever your b value is less than or equal to 0. Now, moving on to numbers 5, 6, and 7. With 5, 6, and 7, we want to simplify each of those expressions, and then our answers must contain only positive exponents. So with number 5, what we want to do is we want to take care of this 3 on the outside. So what we need to do is we basically need to take that 3 and distribute that to the 6 and to the a. So in this case, we're going to get 6 cubed times a to the 4th, but that a to the 4th is cubed. Now we have to simplify this. Here, this is going to be following one of our exponential rules. In the exponential rule that this follows is going to be the power rule. And the power rule says if we have x raised to the power a, and then that entire thing is raised to the b, then you have to take those exponents and multiply those. So here, a to the power 4 raised to the power 3, we have to multiply those exponents together. 4 times 3, that's going to give us 12. So we end up with 6 cubed times a to the 12th. Next we have number 6. Number 6, we have 4 over 3, and that entire thing is raised to the negative 2. Just like we did on number 5 with this 3, what we need to do is take that negative 2 and basically give that exponent to everything in the numerator and everything into the denominator. So when we do that, we get 4 to the negative 2 over 3 to the negative 2. Now keep in mind that our answers must only contain positive exponents. This is following another of our log rules. In this case, we want to look at what happens if we have a negative exponent. If we have a negative exponent, for example, x to the power negative a, what we want to do is we want to take the base, move that to the other part of the fraction. Here we're moving this to the denominator, and we want to change the sign of the exponent. So we see that here we have 4 to the power negative 1 over 3 to the power negative 1. What we need to do is, with this 4, Because we have that negative exponent, we have to take the 4 and move that to the other part of the fraction, in this case the denominator, and then change the sign of the exponent. Similar with this 3 to the negative 2, we want to take the base 3, move that to the other part of the fraction, in this case the numerator, and change the sign of the exponent. Number 7, same process. Take this negative 4, distribute that to the 3, and to the a to the negative 2. So we end up with 3 to the power negative 4 times a to the power negative 2 raised to the negative 4th. Now, before we start dealing with all of these negative exponents, what we want to do is we want to use our power rule here to simplify those two exponents. Because this is the power rule, we have to take the exponents and multiply those together. So that 3 to the power negative 4 will just kind of hang out there. And then we're going to have this a to the power of negative 2 times negative 4 is going to be a positive 8. And then finally, we have that negative exponent here. Keep in mind that this negative exponent is only affecting the 3. We don't have to worry about anything with that a. So we're going to take the 3, move that to the other part of the fraction. In this case, move that to the denominator, change the sign of the exponent, and then that a to the 8th is just going to hang out there. That part does not change. Now, when it comes to the test, keep in mind that we are going to be focusing as well on the 2 other exponential rules. That also includes the product rule. And the product rule when it comes to exponents, x to the power a times x to the power b. If you have 2 of the same bases and they're multiplying, what you want to do is you want to combine the bases, and with the exponents, you want to add the exponents. And then the last rule is the quotient rule. And that's where you have 2 bases dividing each other. And to simplify that, subtract the exponents. So when it comes to exponential rules, these are the 4 that we're going to want to focus on mostly. Now, moving on to number 8, 9, and 10. Number 8, 9, and 10, we want to evaluate each of these logarithms and then justify our answer. So, number 8, we have log base 2 of 8. So when it comes to evaluating these, what we want to do is we want to think about taking that inside number on the side of the logarithm and factoring that down. So in this case, if we take that 8 and we factor that, we're going to get 2 times 4. But then that 4 can factor down to a 2 times 2. So now we can see that 2 multiplies into 8 a total of 3 times. So we can say that's 2 cubed. So what we'll do is we're going to replace that 8 with a 2 cubed. So we end up with log base 2 of 2 cubed. And then after that, we want to use our logarithmic power rule to move this 3 into the front of the log. We end up with 3 times log base 2 of 2. Now, as we talked about in number 3, log base 2 of 2 is equal to 1. And then we're taking that 1 and we're multiplying that with 3. And now we get 3 times 1, which gives us 3. So now number 9 is going to be the same process. That 625 is going to be 5 to the 4th. So if we use that information here and apply that to our log, we're going to get log base 5 of 5 to the 4th. And just like we did on number 8, take this 4, use the power rule, move that to the front of our log, so we get 4 times log base 5 of 5. And again, for number 3, we know that log base 5 of 5 is equal to 1. And that entire thing is multiplying 4. So then we can take 4 times 1, which gives us 4. So log base 5 of 625 is equal to 4. Now moving on to number 10, log base 4 of 16 over 1024. First, notice that this is a fraction inside of a logarithm. So what we want to do is we want to use the quotient rule in order to split that apart into two separate logs. So doing that, we're going to get log base 4 of 16 minus log base 4 of 1024. Now what we want to do is we want to evaluate both of these separately. And we want to evaluate them just like we did on number 8 and 9. So 16, if we factor that down, is going to be 4 squared. So we can replace the 16 here with 4 squared. Log base 4 of 4 squared. And now that 1024, to save some time, is going to be 4 to the 5th. So minus log base 4 of 4 to the 5th. Now again, using the power rules, we want to take those exponents and move those into the front of the logs. 2 times log base 4 of 4 minus 5 log base 4 of 4. Now, just like in number 3, log base 4 of 4 is going to be a 1, but that's multiplying a 2, minus 5 times log base 4 of 4, which is also 1. 2 times 1 is 2. 5 times 1 is 5. 2 minus 3, 2 minus 5 is a negative 3. Now, moving on to the second page. With this second page, this is where we want to focus on all of our log rules. So with numbers 11 through 15, we need to use our log rules here. So starting with number 11, we have log base 2 of x, y, z. So with number 11, this is where we want to use the product rule. And the product rule states the log of a times b, where you have two values inside of a log being multiplied. The product rule says we can split that apart into two logs where they're adding each other. So log of a plus the log of b. Now with the product rule, it works with more than just the two variables. It also works with our three variables. So using the same process with the log rule, we can take this log base 2 of x, y, z and expand that to say log base 2 of x plus log base 2 of y plus log base 2 of z. And that's going to be our expanded logarithm. Now, number 12, log base 4 of x over z. In this case, this is going to be using the quotient rule. Now, the quotient rule is focused on dividing. The product rule was focused on multiplying. The quotient rule is going to be dividing, a over b. Now, just like how the product rule changed multiplication into this addition, the quotient rule will change this division into subtraction. So we have log of a minus log of b. Now, using our quotient rule here, we can apply that to number 12, log base 4 of x over z. So using the quotient rule, log base 4 of x minus log base 4 of z. Number 13, log base 3 of 9x. So again, notice that we have this 9 and we have the x. Those are both being multiplied, so here we want to be using the product rule. And again, you can see the product rule here. With the product rule, we're going to get log base 3 of 9 plus log base 3 of x. Now, keep in mind that our directions say to simplify when possible. we want to simplify this log base 3 of x. So when we're evaluating log base 3 of 9, we're thinking 3 to what power is 9? Well, we can say that 9 is 3 squared. 3 to what power is 9? In this case, 2. So that means log base 3 of 9 is equal to 2. And then we have that log base 3 of x. And then here we just simplified. Number 14, log of 100 times the cube root of x. With this notation, it's a little hard to see, but that 3 right there is with the root. So here we have a cube root. Now, that 100 is being multiplied with a cube root, so the first thing we want to use is the product rule. In that product rule, we're going to get log of 100 plus log of the cube root of x. Now what we could do is we could simplify this log of 100. Remember, when we don't have a base, we have to say that the base is going to be 10. So we're thinking log base 10 of 100, 10 to what power is 100? Here it's going to be 2, plus log of the cube root x. And then in that step, we just simplified. Now, we next need to deal with this cube root. When it comes to roots, we can rewrite that using exponents. So, a square root, this would have the number 2 right here. You see how this cube root has the number 3? A square root would have a 2. Now, if we rewrite that as an exponent, that would be the power 1/2. Notice how the 2 here matches with the 2 in the denominator. So we can do the same thing with a cube root. Now here, instead of the degree being a 2, now the degree of the root is 3. And then just like we do over here with the fraction and the exponent, 1/3. So a cube root of x can be written as x to the power 1/3. Do that over here as well. 2 plus the log of x to the 1/3. And there we just changed our notation. And then finally, we have this 1/3 as the exponent inside of our log. This is where we want to use that power rule. And the power rule says log of x to the power a. We have a logarithm. Inside, we have a number, we have something raised to an exponent. The power rule says you can take that exponent, move it outside and into the front of the logarithm. So that turns into a times log of x. So we want to do the same thing with that 1/3. So take that 1/3, use the power rule on it, move that 1/3 into the front of the log. So that turns into 1/3 log of x. So number 14, we should end up with 2 plus 1/3 log of x. Number 15, log base 2 of x minus 6. When it comes to our rules, we don't have anything that mentions having subtraction inside of our log and then being able to rewrite it. Because we don't have any rules, we're going to say that number 15 is already simplified. Number 15 is already simplified. The reason being is that we have no log rule to expand this logarithm. Moving on to the next page. With these next problems, what we want to do is we want to solve each of these equations which involve logs. Now, when it comes to these equations using logs, we don't want to have the 2 logs on one side. What we need to do is have 1 log on both sides of the equation. So this log base 3 of 10, we have to move this to the other side. So what we'll do is add this log base 3 of 10 to both sides. When we do that, we're going to end up with log base 3 of x minus 4 equals log base 3 of 10. Now, notice that we have a log base 3 on the left side and a log base 3 on the right side. Because we have one log on the left and one log on the right and the bases are the same, that means these inside parts of the log have to be equal to each other. So we can create a new equation just by setting those inside of the parts inside the log equal to each other. X minus 4 equals 10. And at this point, solving for x, you got to add 4 to both sides. And we end up with x equals 14. Now, moving over here to number 18, keeping in mind that this is not properly numbered. Number 18, log base 2 of 3x over log base 2 of 21. Just like with number 16 over here, we don't want the two logs on the left side. So what we have to do is we have to move one of these logs to the other side. In order to do that, we're going to take this log that's in the denominator and multiply that on both sides. So take the left side, multiply that by log base 2 of 21. And take the right side and multiply that by log base 2 of 21. Now, this log base 2 of 21 is going to cancel out with this one here, which means on the left side we're left with a log base 2 of 3x equals 1 times this is that log base 2 of 21. Now, as we saw on number 16, we had the one base on the left, the one base on the right, so we were able to set the inside parts equal to each other. Do the same thing here with 18. Log base 2 of 3x has to equal log base 2 of 21, which means those inside parts have to be equal to each other. 3x equals 21. Now divide both sides by 3. We end up with x is equal to 7. Number 17, 3 log base 5 of x equals 6 log base 5 of 2. Now, with this type of problem, we do not want to use the power rule first. We do not want to take this 3, move it inside. We do not want to take the 6 and move that inside. We notice that 3 is a factor of 6, so what we could do is make those numbers smaller by dividing both sides by 3, which means these 3's are going to cancel each other out. This 6 and the 3 will cancel, turn into a 2. So we end up with log base 5 of x equals 2 log base 5 of 2. Now, this is where we could use the power rule to take this 2 right here and move that inside of the log as the exponent. When we use the power rule, we now end up with log base 5 of x equals log base 5 of 2 squared. And now, just like we saw on the previous two problems, we have one log on the left and one log on the right. You notice how the bases are the same. Now we can take the inside parts and set those equal to each other. X equals 2 squared. And then just simplifying that, x is equal to 4. Now, number 19. With number 19, you'll notice that we don't have any logs in this equation. The bases are not the same, and 456 is not a power of 10. So we cannot rewrite this as 10 to some power. So what we have to do here is to solve this, take the log of each side. So we end up with log of 10 to the power x, as we saw right there, equals the log of 456. Now we're still trying to solve for x. Notice that x is inside of the log as an exponent. We can use the power rule to take the x, move it into the front of the log. X times log of 10 equals log of 456. So at this point we have to get rid of that log of 10, so we're going to divide both sides by that. And we end up with x equals the log of 456 over log of 10. Now, with number 19, notice where our variable is. Our variable is the exponent, and that's attached to the base. So when it came to solving for number 19, we were really focused on that 10 to the power x. Number 20 is a similar type of problem. Look for a variable. Here it's in the exponent, and then there's the base. So this 4 to the power k minus 7 is what we're focused on. We want to get rid of everything else besides that. So that plus 5 that we see right here, we need to get rid of that. So subtracting both sides by 5 will help us solve that. That's going to give us 4 to the power k minus 7 equals 77. Now, all we're left with is the base, our exponent, and then this answer. So we can now take the log of both sides, just like we did over here in 19. Taking the log of both sides, we get log of 4 to the power k minus 7 equals the log of 77. Now, solving for k. This k is in the exponent, so what we have to do is use our power rule to move that out into the front of the logarithm. We get k minus 7 times log of 4 equals log of 77. So continuing to solve for k, we have to divide both of these sides by this log 4, so we can get rid of that on the left. Divide both sides by log of 4. We now have k minus 7 equals log of 77 over log of 4. And then finally, getting rid of that minus 7, we're going to add 7 to both sides. Now we end up with k is equal to the log of 77 over the log of 4 plus 7. Keep in mind that plus 7 is outside of a logarithm, so we cannot add that to the 77 or the 4 here. Now, number 21. Here's our variable x. Here's the base. Everything else besides that we want to get rid of. So we want to focus on that 10 to the power x and get rid of everything else. So we want to get rid of that plus 2, so we're going to have to subtract that first. We end up with 2 to the power 2 times 10 to the x equals 30. Next, getting rid of this 2, we have to divide both sides by that 2. We get 10 to the power x equals 15. And now we have our base, we have our exponent, we have our answer. In order to solve for the exponent, this is where we now have to take the log of both sides. Log of 10 to the x equals the log of 15. Use the power rule to move this x to the front. We get x times the log of 10 equals log of 15. Solving for x, we have to divide both sides by that log of 10 so we can get rid of that. And now we are left with x equals log of 15 over log of 10. Keep in mind, even though you can reduce this fraction of 15 over 10, do not reduce that. You cannot reduce fractions like this when they are inside of logarithms. So do not reduce that fraction. So here x is equal to 15 over 10. Next, we have numbers 22, 23, 24, and 25. For each of these, we want to use this given information to find the exact value of these. Now, kind of what we want to do here is we want to focus on taking these values inside of the logs and factoring those. So if we start with this 9, we can take that 9 and factor that down to be a 3 times 3. Now, 3 times 3, we could think of it as 3 squared. So we know that 9 is 3 squared. Replace this 9 in here with a 3 squared. We end up with log base 2 of 3 squared. Now, using that power rule, move the exponent out to the front of the log. 2 times log base 2 of 3. We know that log base 2 of 3 is 1.585. This is a number that was given to us. So replacing this log base 2 of 3 with that, 2 times 1.585. Now at this point, this is where you need a calculator to take 2 times 1.585. And when you do that, you should end up with 3.170. So that means the log base 2 of 9 is equal to 3.170. Moving on to number 3. Now with number 3, we have this, number 23, we have this fraction here. Because we have this fraction, we want to be thinking about our quotient rule and using that quotient rule to factor that 30 and the 7. So, splitting that apart using the quotient rule, we get log base 2 of 30 minus log base 2 of 7. Now, we cannot factor 7, but we can factor 30. So if we take this 30, we can factor that down to a 6 and a 5. And then that 6 will factor down to 2 times 3. So 30 is going to be 2 times 3 times 5, which means that log base 2 of 30 will then become log base 2 of 2 times 3 times 5. And then that log base 2 of 7 just goes along for the ride. Now, this right here, because we have this multiplication inside of the logarithm, we want to use our product rule to split that apart. Using the product rule, we get log base 2 of 2 plus log base 2 of 3 plus log base 2 of 5 minus log base 2 of 7. Now we have this logarithm fully factored. We can start evaluating each of these logs. Log base 2 of 2 is 1. That is a definition. Make sure you know that. That has to be a definition known. Log base 2 of 3 is a number that was given. 1.585 plus. Log base 2 of 5 is a number you were given. 2.322 minus log base 2 of 7. You were given that number, 2.807. And now at this point, we have to add all of those together. Adding those together, we end up with 2.100. Now, notice that I have those extra zeros here. The reason I have those zeros is so we can have those 3 decimal places. Notice all of those decimals we used are out to 3 decimal places. I'm doing the same thing here with number 23, 2.100. Next, moving on to 24, log base 2 of 12. Just like we did on 22 and 23, we want to take this 12 and factor that down. We know that 12 factors down to a 3 times 4. We do not want to factor this 4 any further because notice our log is base 2. 4 is a power of 2. So we can rewrite this log base 2 of 12 as log base 2 of 3 times 4. Now, we want to use the power rule here to split this log apart. Log base 2 of 3 plus log base 2 of 4. Log base 2 of 3 is a number we were given, 1.585. Log base 2 of 4, we're thinking 2 to what power is 4? Well, 2 squared is 4. And now we just add those together, 3.585. So log base 2 of 12 is 3.585. And then finally, number 25, log base 2 of 486. Just like we were doing with those last 3 problems, we want to take this 486 and factor that down. So 486 we see is even. We can take a 2 out. We take a 2 out, we get 243. Now 243 is divisible by 3, so we can take a 3 out, we get 81. 81 is 9 times 9. And then each of those 9s give us a pair of 3s. Now that means 486, we have a 2, we have a 3, 3, 3, 3, and 3. Now notice that we have 1, 2, 3, 4, 5 of these. Log base 2 of 486 will turn into log base 2 of 2, from right here, times 3 to the power 1, 2, 3, 4, 5. Now inside of this log, we have a 2 times 3. Because these numbers are multiplying, we want to use the product rule to split those apart. Log base 2 of 2 plus log base 2 of 3 to the 5th. Now wait on evaluating this part because we need to use the power rule to take that 5 and move it to the front of the log. Log base 2 of 2 plus 5 times log base 2 of 3. And now you can start evaluating. Log base 2 of 2 is 1 plus 5 times log base 2 of 3. Log base 2 of 3 is 1.585. That comes from right here. And now you take this number 5 times 1.585, multiply that, 7.925, and then add that to 1, we should end up with 8.925. Now, finally, turning to the last page. On our last page, we've got number 26 and 27. Number 26, make a table and sketch the graph of f of x equals log base 2 of x on the axis below. So, we need to both make a table and create a sketch of this. Now, at the bottom of your page, you have that graph. We want to use that graph to sketch log base 2 of x. So, when it comes to these logarithms, on this parent function, we are always going to have the point 1, 0. You always have the point 1, 0. The pattern to fill out this table, start with these f of x values or these y values and add 1 going down the table. We start with 0, we have 1, 2, 3, 4. Now with these x values, what you want to do is you want to look at the base of the log. Here the base is 2. Each time you go down the table, you want to take this number and multiply it by whatever the base is. Because the base is 2, take 1, multiply it by 2, we get 2. Now, do it again. Take this 2, multiply it by the base, which is 2, you get 4. Do that again. Take this 4, multiply it by the base, you get 8, and then 16. So, here's our table. Now what we want to do is we want to take the table and plot it onto our graph. So here is our graph. The first point that we have is 1, 0. So we want to plot the point, which will be right here. There's 1, 0. Next we have 2, 1, 4, 2, 8, 3, and then 16, 4. Now that we have all those points, we want to go ahead and make our graph. We want to connect these together. So we're just going to draw the shape of our log function through these points. Keep in mind that the graph of a log function is going to look a little bit like the lowercase r. Now there's our graph. Make sure we label this so we know what function we're looking at. This is f of x. Now, going back over here to our graph of to number 27. Number 27, make a table and sketch the graph of g of x equals log base 2 of x minus 3 minus 1 on the same axis below. Now, this minus 3 and that minus 1 are telling us what type of what we're doing to this graph. Whether we're moving it up, down, left, or right. So this number on the inside, we'll call this log base, let's do this, log base 2 of x plus a plus b. Now that a value, a is going to be the horizontal shift. Now in this case, if a is positive, if a is positive, the graph is going to move to the left. But then if a is negative, the graph will move to the right. Now, b is also acting as a translation. However, b is a vertical shift. Now, if b is positive, our graph will go up. And then if B is negative, our graph will go down. So in this case, this A value is this negative 3. Because that is a negative, our graph is going to go to the right, and in particular, it will go to the right 3. Now, this value here, this negative 1, is our B value, so we have a vertical shift. Because that is negative, we're going to go down. Go down 1. So what we want to focus on doing next is taking the axes on this graph and applying these shifts to it. So we know we have to take the graph and move it to the right 3. So think about taking this axis here, moving that to the right 3 units. 1, 2, 3, and then drawing a new axis here. Next, we have to move the graph down 1. So think about taking that x-axis and moving that down 1 unit, and then redrawing that. Now, if we started with this point here, we had to move it to the right. Now, with that x value changed from 1 to 4. So now that's a 4. And then we had to move it down 1, so that y value is now a negative 1. So what happened is these x values, we're adding 3 to those each time, but those y values, we subtracted 1. So that's what we want to do with our graph. So over here, the first point was 1, 0. Take this x value here, 1, add 3 to it, you get 4. Do the same thing with this 2. Take 2 plus 3, you get 5. 4 plus 3 is 7. 8 plus 3 is 11. And then 16 plus 3 is 19. Next, we want to take all of these y values and subtract 1 from those. So we took 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. Now, this table here is representing our graph of log base 2 of x minus 3 minus 1. And what we can do is we could use this graph and plot the table on the original axes. So on the original axes, we would go over 4 and down 1. But now notice on these new axes here, this point matches with 1, 0. On these new axes, these dotted ones that we just drew, this would represent the point 1, 0. But on this table up here, we can see it's the point 4, negative 1. Now what we want to do is we want to take this table and continue plotting that using the original axes here. So if we take the point 5, 0, we go over 5, go up 0, there's our next point. Now, on these new axes that we drew, notice that this point is similar to the point 2, 1, which is this point here. So what we want to do is we want to continue plotting these points. Next we have 7, 1, 11, 2, and 19, 3. Now we have all of those points. We can go ahead and make the graph, connect those points together. And there is the sketch of our graph. Remember that we have to label this g of x. So there is our review. If you want to see the PDF of this, make sure you go check out the website. There should be a link there with the PDF of this answer key there. If you have any other questions over the stuff, check out the website. There are other links available. Make sure you're checking those out. Otherwise, see you on Monday. Good luck with your test.